All right, if you're gearing up for your GCSE Physics exam, you've landed in the perfect spot. Today, we're tackling a really key topic from the AQA syllabus, the conservation and dissipation of energy. Let's just jump right in. You know the feeling, right? You unplug your phone, you grab the charger, and it's warm, maybe even a little hot. Now that heat is energy, but it's not actually doing anything useful, is it? It's not charging your phone anymore. So what's going on there? Where is that energy coming from? That's the exact mystery we're going to solve today. To get to the bottom of that warm charger, we have to start with the single biggest rule in energy physics. And trust me, it's not a suggestion, it's an unbreakable law. And this is it, the big one. You absolutely cannot create energy out of thin air, and you can't just make it disappear. It just changes from one form to another. It can be transferred, it can be stored, or it can be spread out, which is what scientists mean by dissipated. But the grand total of energy in a closed system, well, it always stays the same. Now, this is where the term closed system becomes so important. Just picture a perfect thermos flask for a second. In an ideal world, in a truly closed system, no energy can get in and no energy can get out. So the total amount of energy stuck inside that flask, whether it's heat energy, chemical energy, whatever, it never changes. It just shifts around from one type to another. Okay, hold on. If energy can't be destroyed, then why are we always talking about wasting energy or saving energy? If it never actually vanishes, what's the big problem? And here is the absolute key idea. The energy isn't lost, it's just spread out. It's been converted into a form that's not useful to us anymore. That warm phone charger? The electrical energy has turned into thermal energy and has just dissipated into the air and the desk around it. The energy is still there in the universe, sure, but you can't get it back to power your phone. That's what we mean by wasted. A light bulb is the perfect way to picture this. The whole point of a bulb, the goal, is to turn electrical energy into light energy. That's its useful job. But we all know that light bulbs get hot. That heat is also an energy transfer, but it's the unwanted one. It's the dissipated energy, the waste product of the system. So how quickly does all of this wasted heat escape? Well, it all comes down to a property called thermal conductivity. Something with high thermal conductivity, like a metal spoon, lets heat travel through it really fast. But something with low thermal conductivity, like the wool in your jumper, is really slow at transferring heat. So bottom line, if a material is a bad conductor, it's a great insulator. So now that we know the enemy is this dissipated energy, we can actually start to fight back. The whole game is about one thing. How do we cut down on these unwanted energy transfers? How do we stop that useful energy from just spreading out and becoming useless? And we have two main weapons in our arsenal. First up, for anything with moving parts, we use lubrication. A bit of oil reduces friction, which means less kinetic energy is wasted as heat. And second, we use thermal insulation. This just means wrapping things in materials with low thermal conductivity to trap heat where we want it. A house is the perfect real-world example. We build them with thick walls, we put special glass in the windows, we fill the loft with foam or fiberglass. Why? It's simple. All those materials are terrible at conducting heat. They massively slow down the rate that heat escapes from your warm living room into the cold air outside. And for everyone with that AQA exam on the horizon, listen up. This is not just some random theory. This is the why behind required practical number 2, the one where you investigate which materials are the best thermal insulators. If you understand this stuff, you'll understand exactly what's going on in that practical, and that's where the marks are. So we know some energy is always going to be wasted, right? But how do we actually measure it? How do we keep score and figure out how good a machine is at its job? Well, we calculate its efficiency. Put simply, efficiency is just a number. It tells you what fraction of the total energy you put into a device actually comes out as the useful stuff you wanted in the first place. Okay, this is the first equation you absolutely have to know for the exam. Efficiency is just the useful output energy divided by the total input energy. That's it. Think of it as the good stuff you get out compared to all the stuff you had to put in. And you know what? Because power is just the rate at which energy is transferred, the exact same logic applies here too. You can also work out efficiency by dividing the useful power output by the total power input. Either equation will get you the same answer. So let's make this real. Imagine you put 100 joules of electrical energy into a motor. Now, if you get 75 joules of useful kinetic energy out of it to make something move, but the other 25 joules are just wasted as heat and sound, well, its efficiency is 75 divided by 100. That's 0.75. And we usually write that as a percentage, so we'd say it's 75% efficient. Okay, deep breath. We've done the law, the problem, the solutions, and the math. Let's boil this all down into your ultimate exam cheat sheet. This is everything you need to walk into that exam feeling confident. Here are the non-negotiables. 1. Know that law of conservation of energy backwards. 2. Understand that dissipated energy is just the proper science term for wasted energy. 3. Be able to explain how lubrication and insulation work. 4. You've got to memorize both of those efficiency equations. And 5, and this is a classic exam trap, so please remember this. Efficiency has no units. It's just a ratio, so it's a decimal or a percentage, never joules or watts. So the next time your laptop charger feels a bit toasty, you'll know exactly what's happening. That's dissipation in action. And it leaves us with one final thought. Look around your house. What do you reckon is the most inefficient thing in there? An old games console? A dodgy fridge? Maybe even your kettle? Once you start looking for it, you realize this stuff is happening everywhere.